Hi, and welcome to our fourth tutorial in the series, Monty Hall and the Python. Again, if you need to know what the Monty Hall problem is, go back to tutorial number 1. We have successfully now simulated going through the Monty Hall problem, and we made it in a loop that we could go through 10 times, and we could tally our results. That's what we did last time. So now we're going to automate some of our responses so that we can go through it even more efficiently and find out some statistical significance to the answers that we're interested in. Because one of the questions we really want to answer is, are you better off by switching your answer at the last moment once one of the wrong choices has been revealed to you? And if you look up this problem on Google, what you'll find out is that yes, you're better off switching your answer. But if you want to know why, you'll keep going, and we'll continue programming this simulation together, and we'll find maybe convince ourselves. All right, so we're going to start over here, and now instead of range 10, we're going to say, we're going to make a new variable, say, how many sims, and we'll still call it 10 for now, but we will change it here. And if you recall, we also were using this 10 figure at the very end because we said we were right some number of times out of 10 times. So we'll just say, how many sims? Okay, so you were right. Tally out. In fact, we'll add a new line. I'll duplicate this line. I use Control D in Notepad++, and then I'll say tally. We'll say 100 times tally divided by how many sims percent of the time. You were right. So many percent of the time. Okay. So that should be helpful information there. That's a helpful calculation. All right. So now how do we get rid of some of the fluff in here and make the thing go a little more efficiently? Well, one way we can do that is to say, I chose A every time out of simplicity. We can make my choice, instead of it being input, so what I did is I duplicated that line just so I could keep the old input, and then I used a Control Q to mute it, which is to put a comment there at the beginning, which is the hash mark or the pound sign, whatever people call it these days. So instead of it being an input, we'll just use the choice function again, all right? So my choice will be sample choices 1. And again, we'll do 0. So in this case now, my choice will be a sample of the choices, and we're just choosing one choice, but it doesn't matter what my choice is. Okay, so we've picked the correct choice, my choice. They're chosen in the same way from the same set of choices. Okay, now we have another set of input here for switching our answer. So if we want to test, now we can just get rid of all of this. I'll use the Control Q again to make that muted, and we can say switch is equal to false. We can just start off by never switching our answer. All right, so remaining choices will still be, this is correctly named, and if switch, our new answer is the remaining choices. If not, the new answer is my choice. How did you do? If you got it right, we +1. And we don't need to print this every time. And so if we don't print that, we will we'll get rid of all of these print statements. And what that will do is just make our code run a lot more cleanly. So let's save this as, and we'll save it as the Monty Hall tutorial number 2. And we'll go in our terminal window here. In fact, I can make this bigger too, I suppose. And now instead of 0, we want to go 2. Oops. All right, so we're going to Python Monty Hall tutorial 2.py. I was right 2 out of the 10 times. I was right 20% of the time. Okay, well that ran really fast. Why don't we do 100 simulations? So we just changed 10 to 100. And now we'll see. I was right 33 out of 100 times, or 33% of the time. Well, that's interesting. But that's what you would expect. By doing one choice out of 3 options, you would expect to be right 33% of the time. Okay, so that makes sense. I hope that you would agree that now, there's no bearing on Monty Hall. He revealed something, but we stuck firm in our choice. And so statistically, this is bearing out just exactly as you would expect. Now, I would expect if you did this 1,000 times, it's not going to be exactly 333 because of randomness. But we'll do it 1,000 times and just see what happens. All right, 339, 33.9% of the time. So this is showing a very robust answer that conforms with what you expect for not changing your answer. So then here comes the easy way to check what happens when you do change your answer. So we'll just change switch to true. All right, now switch is always true. And what will we see? Okay, you were right 650 out of 1,000 times, or 65% of the time. Well, that's better than 50-50. That's better than average. Let's see if we can run it. We'll run it 10,000 times. That runs really fast. I don't know if there's any limit to how fast we can run this thing. You were right 6,649 out of 10,000 times, or 66.49% of the time. Okay, so why do you think that is? Why is it that if you switch your answer, you're right 66% of the time? If you don't know, then in the next tutorial, I will show you using some of those graphical images I used at the beginning. I think they help hash it out. But what we're going to do following this, starting from here on, is we're going to generalize this and say, well, okay, this is a funny result for 3 doors, but what if we had 4 doors? Or what if we have 100 doors? And what if we opened more than one door? What if we opened 50 doors after we had 100 doors, or something like that? And so hopefully, by generalizing this problem and taking it to some extreme limit, that will help you, if you don't already, to understand why it is that switching your answer helps you to be right more of the time. So thank you for watching this tutorial, and I hope that we will see you in the next one.